This video will cover the ideas of polarization, but mainly focusing on stationary, also known as standing waves. So how these are created, what nodes and antinodes are, and then we'll look at a few applications as well. And the context of this is lots and lots of musical instruments. So acoustic instruments such as a guitar. So when you pluck the string on a guitar, you set up a standing wave and you have multiple standing waves known as harmonics, and you get this wonderful rich sound. So this is also true for wind instruments as well. So lots and lots of applications in music. So what is polarization? So if we have a wave such as light wave, which is an electromagnetic wave, then the vibrations are in all directions. So we might have vertical vibration, we might have horizontal vibration, and then every other possible angle, so not just the few shown here. So an unpolarized transverse wave will vibrate in all possible directions. Now if we channel that through a filter, which is aligned vertically, then you can see that only the vertical vibrations will pass through. So we have over here just the vertical vibrations. All the other vibrations are horizontal, and all the other angles were not able to pass through this vertical gap. So this is known as a vertical polarized wave, or a plane polarized wave. Now there's various demonstrations of this, which you might have seen in lessons or you might see on YouTube. So Polaroid filters and visible light is a simple one. You can also get microwaves, which are polarized to start with, and then you can rotate a metal grid which can show the direction of polarization. Various applications, so Polaroid glasses reduce glare. You can also use Polaroid filters to show stress in materials and identify minerals in rocks. So in terms of what you need to know for the exam, most exam boards just need to be for you to have an awareness of what polarization is and what is meant by plane polarized waves. So waves that can only vibrate in one direction. Okay, so what is meant by standing waves? So you might have seen this demonstration of a standing wave. You can get a piece of wire and a vibration generator. And what's actually happening is a wave is being sent along the string and then is reflecting back 180 degrees out of phase. So we actually have two waves. We refer it to as the incident wave and the reflected wave. And these two will interact. And you can see that the blue and the green wave are moving in different directions. So they're constantly going in phase and out of phase. So where they meet in phase, as we can see here, then we get maximum amplitude. So the two add together to form what's known as an antinode. A little bit further on, they'll meet out of phase. So we get a node, we get cancelling out. And then further on, they'll meet back in phase again. So we get this antiphase antinode. So we've got this constant interaction between the two waves where we have this maximum displacement in the middle. This is known as an antinode. And the midpoint here, the node, they will always cancel out. So we're getting this constant change of displacement. So as we've said that standing waves appear to travel, they are not progressive waves. So all waves we've looked at up to this point are progressive waves because they move from a point through space or through a medium to another point. But standing waves are effectively trapped between two endpoints. So they're different to progressive waves. So how do we represent standing waves diagrammatically? So it's all about drawing loops. So we tend to draw a loop, which means the lowest point and the highest point of the antinode, and then we get a node where we have zero amplitude. So we might have 2 or 3 or more loops as shown here. The wavelength is 2 full loops. So from this point here all the way to this point here. And you can see if we draw a normal sinusoidal wave, that would represent our wavelength. Okay, so we've got an antinode, a node, and an antinode, a node, and an antinode. So if we have an oscillating string, then we have a node at both ends, and we have an antinode followed by a node. So we have these kind of loop, adjacent loops. Importantly, each sector is 180 degrees out of phase with the adjacent loop. So if we look at this left-hand loop here, all of these parts are moving down, and the right-hand loop, all of these parts are moving up. So these two waves are 180 degrees out of phase. That is different to a progressive wave, where we have a gradual change in phase all the way along from 0 to 360. So that's one key difference between standing waves and progressive waves. If we just have a single loop, as shown here, this is known as the first or fundamental harmonic, and we can see that one loop is half a wave. So one single loop, if we knew the length of the wire which was oscillating, that would represent half of lambda, half a wavelength. If we have two loops, that's known as the second harmonic. So in this case, the full length of string would represent a full wave, so this would be the wavelength. And then we could have three loops would be the third harmonic, and so on. Okay, so various scenarios we need to consider. So we can have standing waves in tubes. This happens a lot in musical instruments. So we have a closed tube. What that means is it's open at one end and closed at the other end. So at the closed end, we have minimum or zero vibration, so that's going to be a node. At the open end, we have limited restriction on movement, so that is an antinode. So the shortest fraction of a wave we could have would be a node and an antinode, which would be a quarter of a wavelength, it's half a loop. So if we then increase the length of the tube, the next standing wave we could have would be node, antinode, node, antinode. So you can see this is 1.5 loops, or 3/4 of a wavelength. So what we could do is use this to measure the wavelength and therefore the speed of sound. So if this was a practical, I could measure the length here, L1, and here the length L2. But in actual fact, the antinode is slightly above the top of the tube by what's known as a correction factor C. So in actual fact, lambda over 4 is equal to L1 plus this extra bit, C. And then also over here, 3/4 lambda is equal to L2 plus this extra correction factor C. So measuring C is very, very difficult to do. We don't know what it is. However, we can see that it's the same C in each case. So if I subtract this formula, if I subtract the left-hand formula from the right-hand formula, then we end up with L2 minus L1 is equal to 3/4 lambda, take away lambda over 4, which is lambda over 2, and the C's cancel. So we could use this method for working out the wavelength of the wave we were looking at, and if we know the frequency, then we can calculate the velocity, V equals F times lambda. Another variation is an open tube. So open tube means open at both ends. So this might be an organ, perhaps, a musical instrument. So you might have open at both ends. So we must have an antinode at each end. So if we think what's the smallest fraction of a wave we could have, which has an antinode at both ends, it must be antinode, node, and antinode. This is the first harmonic, or the fundamental harmonic. And we can see that I've got half a loop here and half a loop here. So in total I have a full loop, which we know would represent half a wave. So if I was to measure the length here, that would represent half the wavelength. The next harmonic, once again, we've got an antinode at both ends. In this case, we're going to have antinode, node, antinode, node, antinode. So this is the second harmonic. We've got half a loop, and half a loop. So two full loops, which represents one wave. So again, we could use this to work out either the wavelength and therefore perhaps the velocity of the wave if we know the frequency. Okay, let's look at a worked example. So we have a string of length 60 centimeters. We're given the frequency. It tells us that it vibrates in its fundamental harmonic. So the fundamental harmonic is one loop, which we know already is half a wave, or half the wavelength. So we can calculate the wavelength. It must be 2 times the length that we're given. So 0.6 times by 2 is 1.2. Part B, if we know the frequency, we're given that, and we've just calculated the wavelength, then we can work out V equals F times lambda. We can work out the speed. Now the speed or the velocity of the wave is determined by the type of string, so the mass per unit length, and also the tension. So if those are fixed, then the speed does not change. So it says what frequency is needed to produce a standing wave in the second harmonic? Well, we know that the second harmonic is 2 loops. So now a full wave is on the same length of string. The length of string hasn't changed. So the wavelength is now 60 centimeters or 0.6, which is half of what it was before. Rearrange the wave formula. F equals V over lambda. The 180 is the same as before, that hasn't changed. So divide by 0.6 and we can calculate the frequency. So this is a pretty typical question. This will be quite a straightforward question. thinking about which harmonic we're referring to and applying the wave formula to solve the problem. Okay, here we go. Now it's time to answer some questions. So question 1, 2 and 3, pause the video, have a go at these on a piece of paper, and then when you're ready you can check your answers on the video. Right, question 1. So all we really need to know about polarization is what is it, which waves can be polarized, and maybe what it can be used for. So these are our basic notes. So polarized light oscillates in one plane only. This is what we mean by plane polarized. That could be vertical or horizontal. Only transverse waves can be polarized, and typically we're referring to Polaroid filters, and they're used in sunglasses to reduce glare, and there's other applications as well, such as looking at stress in materials. The most important set of notes is question 2. This is a very typical question in the exam. Typically 4 marks, possibly 6 marks. So the initial wave, the incident wave, travels along the string and is reflected at the end, and it comes back 180 degrees out of phase at that point only. And then we have these 2 waves interfering. The reflected wave interferes with the incident wave. That's the key term there. Where they meet in phase, we get constructive interference, we get an antinode. Where they meet out of phase, we get destructive interference, and we get a node, and that's minimum or 0 displacement. So this is probably the most important set of notes or bit of information from this video. Okay, question 3. So the first thing to do here is probably to draw what the wave looks like. It says the third harmonic, that means 3 loops. So we can see that we've got 3 loops here. We know that 2 loops represents a full wave. So this is 1.5 waves. So we could hopefully see that if this is 90 centimeters long in total, then 2 loops is 2/3 of that. So that's going to be 60 centimeters. What is the speed? That should be straightforward. V equals F times lambda. We're given the frequency. We need to work in meters to get meters per second. So 125 times by 0.6 will give us 75. Then part C, very similar to what we saw before. If it's the same tension and the same length and the same type of string, as it says in the question, it's the same wave speed. Therefore, we can just rearrange the formula to make F the subject. F equals V over lambda. But we need to work out what the lambda is. So the fundamental harmonic, that means 1 loop. So we've still got a length of string which is 90 centimeters, but now we have a loop on it, just a single loop, which we know represents half a wave. So we need to multiply 90, or 0.9, by 2 to get the length of a full wave, and then we can substitute the values and we can calculate our frequency. Okay, so a quick review of the key points. So polarization, the key ideas on polarization, and standing waves, the explanation of how a standing wave is formed either on a piece of string as it vibrates, or air in an open or closed tube. There's also a Kahoot, which will give you a quick recap of this. The details should be in the description below the video. Well done everyone, see you next time.